slides, I would like to talk to you about the project. So I'm told that we're going to, or we should have, a sort of a cook-off, a bake-off. I know that many of you are preparing very hard for the data set, and in the project we are going to sort of give you the opportunity to talk about your data set. Okay? Talk about the task that you are thinking of. Okay? And I think there are close to 20 proposals, and so there are actually there's too many to talk about in one class session. So we've asked people who, or the teams who are preparing the data set to make a small video about their data set, tasks, how much data they have accumulated, and the sort of performance that they're gaining on that data set. And what we're going to do is the staff and me, we're going to look at your videos and pre-screen some of the teams, okay? And then maybe select a couple, and those teams will present in class, okay? And as you know that if your data set is selected, then everyone in the class will choose one of the data set for the final project. Okay, so and the schedule is we're going to do this. You send in the videos, and Monday. Monday was it? Next Wednesday, right? Next Wednesday. We're going to give you the opportunity to talk about your data set. Okay, so any questions? Yes.
Which format of the video should you like do presentation on that video, or?
If you can, yeah. So because I'm going to, because there's too many, right? There's too many. So I'm going to look at those and say, oh, this team has too few data, or they're having problems, or I'm going to try to pre-screen as the best that we can do, the staff.
Okay. Shouldn't we make the video which is much different from presentation, like video containing some information without the video of us standing in front of our slides?
Just give us, I think the video, the purpose of the video is to give us some indication about the data set that you have accumulated. Okay, and so not only that, but the task, and also the quality of the data set. The quality of the data set usually is has to do with the algorithm that you apply on that data set, right? And also another, if everyone has very good data set, good quality, lots of it, then we'll probably have to think about uniqueness. Okay? Is this data set unique compared to all other data set that has been proposed before? Okay? I mean, the purpose is to cut down on the number. Okay, so that's the purpose. Okay, I'm going to today. If you look at the syllabus, I have like bias variance decomposition, which is a very important concept in machine learning. Very, very important. It's the way how you look at the error, the prediction, and ground truth square difference error. How do you, where does that error come from? And it seems like it's coming from or due to these two elements. Okay? And before I talk about that, I need to sort of talk about regression first. Okay? We've talked a lot about classification. I want to talk about a new topic, which is called regression. Okay? So I'm going to talk about regression and then come back to bias variance decomposition. Okay? And then in the syllabus, bias variance decomposition comes prior to linear regression. Anyways, here it goes. Please ask questions. Okay, as usual, regression. What is regression? Regression is a supervised learning task. Okay, and I hope everyone understands what a supervised learning task is. You have data and label in the training set, and in the test set, you're trying to figure out the label of the data. Okay? So, and let's try to. So regression, supervised learning, and what is the so determining the mapping function from the input to the output, and the relationship. So you're trying to find in the wiki. This is some words from the wiki. I might have to change this. Relationship between a dependent variable. That's a word that is dependent variable and one or more independent variables. Okay? Independent variables are the inputs, and dependent, the label, the output, is dependent on the input. Okay? So they call it dependent variable. So you want to find that mapping function. Oh, this is very similar to classification. What is the difference? What is the difference between classification and regression? And the only difference is in regression, the label is numerical. It's continuous. Whereas in classification, label is discrete. Or we call it categorical. Okay? Categorical, discrete, they're all the same. Okay? And there are a finite number of them. That's the big difference between regression and classification. And through regression, one understands how the typical value of an independent variable changes when any of the, oh, sorry about this, oh, I got a lot of typo here. Typical value of a dependent variable changes when one of the independent variable is varied. Okay, so this is, while the other independent variables are held constant. So we want to find the effect of changing one of the independent variable. How is that going to affect the output? And we will see, this is something that you may not see right away. Regression analysis estimates the conditional expectation of the independent variable given expectation of the dependent variable given the independent variable. Okay, and I'm going Your prediction is the average value, so the prediction. What do I mean by prediction? I mean the output of this regressor is the expectation of the label given the input. Or another say, it's the average label of X. Yes. Simple as that. Okay, and I'm going to try to prove this. And this makes sense, right? Right? So, a mathematical formulation, in machine learning, as I said in the very beginning, you want to be a little bit mathematical, okay? Because mathematical is exact. Rather than saying things in many, many words, like I've said this thing in many, many words and I've made lots of mistakes already, you want to do something like this. Given data, training data, of course, where xi is some coming from some domain, big X, but the y is usually a real number, the label, and the goal is to predict the value for y for a given X. And I also have a definition at the very beginning. An example. Okay, always example, very, very important. Given the weight and height of X, how long is he going to live? That's like a number. Given the weight and height, what is his gender? That's a classification problem. Regression is how long is he going to live? So it's like a number. Okay? Now, I'm going to be talking about this very important function in regression. We're going to be, what type of classifiers have we looked at so far? We looked at a fair number of classifiers, like the perceptron is one of them. And then we looked at, before we looked at perceptron, we looked at this type of classifier. Oh? Oh yeah, the decision, forget about the decision tree. This is also maybe. The classifier that we looked at, perceptron, is a linear classifier, right? Linear classifier. We looked at linear classifier. A line that the decision boundary was a line separating the two classes. A line, right? We're looking at a line. Here, we're going to look at linear classifiers. Okay? But there's a twist. There's a twist. The output is linear combination. So W here is sort of the coefficient or weight. Of some function of the input. Okay? So this looks like very much, I mean, we looked at classifiers that did this. Whoa! Linear classifiers. Can you give me the form of the linear classifier? Just to, what is the form of the linear classifier? I mean, what? Y equal theta. Okay, very good. That's very good. And I'm going to assume that the bias is inside there. I don't. Is this the classifier? Linear classifier. Is this right? If I gave you an exam problem, true or false, linear classifier is this. What would you say? Oh. I will give you, I should the exam. This will be wrong. You would have to have. Yeah? Is it positive or negative? This is a linear classifier. This is very important, right? Is this value positive or negative? Okay. Well, anyways, this is where the linearity comes from. Here, there's no need, and it looks like that. Okay, the W is the weight, okay, the theta, so to speak, and it goes through some function, phi. So let me just. Write this thing here and here in a different way, okay? So it takes the input, x, and we want to find the label. But we take the x and put it in these functions, phi, blah, 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 phi 0 through phi p. And then I'm going to take inner dot product with the W. Linear. And usually phi 0 is value 1. So what is the bias? That will be the bias. That will be the bias, right? Then so that's it. Now I need to define what the fees are. What are these fees? Why is there a fee there? Okay, what are these fees? One example of a fee let's say the input is d-dimensional. So if I'm talking about weight and height, d will be 2. Phi, this big phi, is just the x. Okay? So will be my label will be just taking the linear combination of the weight and height. If I define phi this way. Okay? It just spits out x. If I define each of the phis this way, what is that? Phi j is x value to the power j. Okay, here I'm talking about scalar. X is a scalar, it's not a vector. Then what is y? So in this case, in the first case, y will be the linear sum that would be that. If phi j is that, then y is what? It's just wi xi to the power j. Okay. Even though this looks like a linear operation, we're actually doing, the prediction is actually polynomial. Other phis are Gaussian. It could be Gaussian. It could be a sigmoid. Or each one of them can be one of these Fourier coefficients. And this is not a signal processing. It's not EE202, which you loved, and you want to see it again and again. I won't give you the pleasure, so I will not talk about it too much, because you love to see that Fourier transform again, and you're interested in that, but I won't give you that pleasure. Okay? And there are other basis functions, and I hope you've learned all this. Okay, so this linear basis function is an extremely useful and versatile function. It's a linear weighted of the basis to make the prediction. It's a linear, so the regression, although slow. So we'll talk about this a little bit later. So the prediction seems to be linear, but it could be various different things. As you can see, we may be fitting a polynomial in this formulation. Okay. So, if you think this is linear, so here is x, here is y, and if you think this is the training data that you have, then you will do this. This will be a good fit. Or if you, in 2 dimension, you have x1 and x2, and they're lying in some plane, then this will be a good way to do this. If I think that x and y, that, then this polynomial fit will be better. And you can take it. Okay, so that's that. Also, this linear basis function, we don't actually assume that the model, this is the model, that this model is actually true. We choose this model because it's computationally expedient, meaning because it's linear, or we may have too little data to use a complex model without overfitting. Okay, so there are two reasons why you use linear basis function. One is computation. You're going to do linear. And we'll go through this, hopefully, the computation is. And because you have little data. Okay. Now, this equations you may look and you say, oh no, there's too much math in this thing, and there are going to be some math involved in regression. Okay? So it's good to stay awake. I know that you're all sleepy. You know, I went to bed around 3 yesterday. Okay? And when I woke up, I thought it was going to be 5 or 6. No, it was 8:40. So I had to rush to come here. Okay? And I have the benefit of standing up so I don't fall asleep. But you, sitting down, you know that it's my voice is no good. It's too low. I should have a sort of like a more high-toned voice, so that you can wake up. But I don't. I'm sorry about that. But today you have to try to stay awake, okay? Because today is a very important day, okay? That you need to. I need your focus. So this is, you know, you have some data. You have some data, and you look at it, and you assume that it's going to follow some function, fx. It's deterministic. Okay? There's no probability. It's deterministic. It's a linear line, let's say, or a quadratic. Something like that. Or it's like a sine. Okay? But not all points in your training set is going to lie in this f of x. There's going to be some error. And that error is modeled here with an epsilon. Okay? So I'm going to, let's look at some. How do I get this thing into some finer? So, you know, you have some points here, very easy ones. So those are data points. And hey, you say, oh, it's linear line. Oh, Jesus. Sorry about this. Sorry, let me just erase this. So these are the points. So, oh, guys, and you say, oh, this looks like a line. So I put the line, so it doesn't look like a line. So fx in this case would be some a, oh, I'm use w here, w1x plus wc. In a line, but it doesn't fit those points exactly. Oh? And the other ones are going to be just epsilon. And we're going to model that as epsilon. That's how I. But you know, you can. I've made an easy example. Fx can be a sign, and the points are not going to be exact. So, how should we think about this epsilon? How should we think about this epsilon? Well, it's error, but what kind of an error? Usable? Irreducible error. Okay, I don't want to go into that. Right? Just think about it as it could be a measurement error. You assume that it's a measurement. Oh, this is coming from a line, but as I'm getting the data, oh, there is some error in the measurement. I could think of this as a measurement error. Or think of it as what? A model error? Oh, my model is not my f of x. When I say model, I mean that this is f of x. That's not exact. So there is some error. Or as I'm getting the data, there is some error. It's truly fx, but as I'm getting. So think of it wherever you way, whichever way. Okay? And very important, in many, many cases, this epsilon, so f of x is deterministic, right? Deterministic, just you put x in there and then you get some y. F of x, right? But the epsilon right here, is the epsilon going to be same all over here? So you're going to get epsilon for this one, and you're going to get an epsilon for that one, and another epsilon. Are the epsilons going to be same? It's very, very important here. You know that the epsilon, the error, is going to be different for all the data, right? How do we model this? How do we model this? We say that this epsilon is coming from some distribution. It's a random variable. If I look at the epsilons only, oh, the epsilons, some epsilons here, some epsilons here, here, but most of them are here. Sparse here, very few of them are. So, so I can just put a sort of like a distribution over it. So that's the probability of the epsilon. So this epsilon is coming from some distribution. It's random. It's we call it stochastic. Stochastic. It's a random variable. Okay? F of x is what? Deterministic. Epsilon is a random variable. It's coming from some distribution, and it could change. A very, very important concept. And here, let's assume that epsilon is coming from this. What is this? With mean 0 and variance sigma squared. And that's how I'm going to model my data. I see training data and I say, oh, that is going to be in some linear form, but the data is not right on the line. The error is going to be some stochastic thing. That's my model. Okay? Understanding this equation right here. Very, very important. You should be comfortable with this. Okay? So, now, let us assume that the criteria for error. So I cannot do this. Someone said this thing. This is an error, and the best I can do is try to get this f of x. I'm giving. Okay, so here is the equation, and what's going to happen is I'm going to get some data right here, some x value. I should be getting that. So for some x, I should get that. That will be the true value. But what I'm shooting for is this value. Because I'm shooting for that value. And I'm going to have some error. I know it's very difficult to stay awake because it's like torture, right? So I have this. So this is a training set. The blue ones are all the training set. I had this x value. What is the y? Well, the true y is right here. What I'm trying to shoot for is that one right here. Okay? What is that? That's this value I'm going to call as f hat of x. Okay? Why do I put a hat right here? Because it's an estimate of fx. Estimate of fx from the training data. I'm assuming that the data, the ground truth is really that plus that, but I don't know this. I don't know what f of x is. And I'm going to try to estimate that. This one. And I'm going to call that f hat of x. Okay? And let's say, in machine learning, what's a very important thing? The first one thing is the hypotheses. Okay? What kind of a function am I going to use? But what kind of hypotheses space are we thinking about? The linear basis function, linear, right? Linear basis function. Then what's another very important thing in machine learning? You know, you have training data, test data. What is it? I didn't talk about what's in the framework. What's also very, very important? Loss function. What is my criteria for good and bad? Huh? There are many ways to define this. Okay, usually classification is 0, 1 loss. Regression, one common loss function that we often use is mean square error. What is mean square error? My prediction, I've explained what this hat, why I put a hat there, right? I'm going to estimate f of x. Okay. What is that? The true value, true label of x. Take the difference and square it. And what's this expectation? What is machine learning about? Machine learning is about for all data. For all, not only training data, but you want to do it for data that you haven't seen. Huh? And this data lies where? It's coming from where? Where is x and y coming from? It's usually a pair, right? Where is that coming from? Very important concept. It's coming from, we assume that it's coming from some distribution. Some probability distribution, joint probability distribution. X and y is coming, we don't know this, but we assume that there is this distribution, right? Not just only x, but x and y pair coming from some distribution that we don't know. The only thing we have, instead of probability, what do we have? We only have data. Okay, everyone says it's very good. So, this square, I want to minimize this over all possible x and y. You give me any x and y, I want to minimize this in the average sense. So this can be written this way. This is just the definition of expectation, right? Okay, everyone understand this? Model, understanding this. Now if you try to first, many books just start with this without, you might not really understand what this is. You have to really, understand this problem, this model. It's a little bit more, and then this. Everyone understand this? From here to there, this is basic probability. But when I say basic probability, some people say, oh my goodness, I don't know basic. I cannot take this course. And that's why I think many students have left us. Many students have left us because I've said these words, okay? But it's not, this is, you may have forgotten it. Just look it up to page 1 of the probability, or no, I don't know, page, early parts of the probability. This is, okay, so you understand what this is? This is our prediction. This is ground truth. And that data, x and y, is coming from this distribution that we don't know. The only thing we have is data. And of course, machine learning is about generalization. What is generalization? Doing well on data that you haven't seen, on test data, right? So, I'm going to, the joint probability is split into the marginal probability multiplied by the likelihood. Okay, this is probably like page within 10 or 20 of the any probability book. Okay? So you say, oh my goodness, I'm going to drop this class. Don't drop it. Just read like 1 or 20 pages of probability. Or if you look it up the internet, it's probably rated very at the top. Okay? There it is. So, hey, how do you, this, you don't really have to understand this. This, right over here, is the definition of that. And the outer one is that. Okay. It's the x, if x is given, this is the conditional probability of y, and then that will be sort of the loss. That's this. This is given x, the loss, and that's the average. And the outer one is overall average values of x. Okay? All right, now, what will be the criteria? Now, so this was the loss. This is the loss that this is mean square error. How do we call it? MSE. This is prediction. So what should we do? This is the loss. What do we want to do with the loss? We want to minimize it. Okay? Minimize it. Now, from the x and y, why do we do this? Why do we do this? I want to explain this. X and y. This is why I use the word one is dependent and one is independent. Huh? Which one is the dependent one? Because y is dependent. X can be anything, right? Just or either within the range. So if I've defined this way, x is some independent variable, some value, and we're trying to make a prediction. And this is the probability. This is overall x. So I've sort of decomposed this thing into independent and dependent. Independent can be any variable. Usually, independent also variables are uniform. You know, anything. You know, but in some situations, you may have lots of x's concentrated in some region. Well, anyways, I want to minimize this. How do I minimize this? If I can minimize this inside, then this will be minimized as well. So what does this say? This is saying, you give me some value of x, any x, over the subdistribution, and I want to predict very well. Any x. Well, just think of it this way. What am I trying to say? If you look at this, what is this value right here? This is probability, right? What is this? It's a positive value. 0 to 1. No? Think of it this way. If you don't understand that, what independent and dependent, this is positive function, right? This positive function. And then you have something here. So if I minimize this, then I'll be minimizing the whole thing. Does that make sense more? So let's just say minimizing that equates to minimizing this. I just want to get that over. So how do I do this? What is my goal? What is my goal right now? Of all this math, what I'm trying to do? I want to minimize the mean square, but why? To get what? F hat, right? We need to think about it. Oh, I need to find out what f of hat x is. Right, that was the goal, right? Minimizing the loss. So what is my prediction? If I minimize the loss, what prediction is that going to lead to? Right? That's the thing. We had a model, let me just say, we had a model, it's too early in the morning, we had a model, then we also had a loss. We're trying to minimize this loss to get what? To get our prediction, right? So what's the prediction here? F hat. So I want to minimize this, as I said that, minimize is the same as minimizing that. So let's say my prediction, I'm going to call that C here. Okay? I'm going to call that C here. It's not too difficult. Just C. Because C, what is the C argument? C, what is the C that minimizes this function? Okay? Right?
C equals 1.
C is this f hat. I don't want to use this as this function because I'm going to take the derivative of this. And you say, oh, is this what the derivative of a function? Then you have to take chain rule. And I don't want you to be thinking about that. I just want you to be thinking about f of hat x, given some x. You're given x. This is what it means, right? Given x, some x value. What is my prediction going to be? X is known. Okay? X is known right here. Given, x is known. Bing, 5, 6. What is my prediction? Okay? Understanding this math a little bit. Okay. Given x. And so I'm just going to say, rather than think about it as a function, I'll just think about it as a number, c. Okay? I feel more comfortable that way. Maybe for you not, maybe not. C. Okay? So how do I do this? Oh, usually you want to find the top point. What do you take? You usually take the derivative, right? Derivative. So I take the derivative with respect to C in this case. If I wrote a function right here, f hat x, you may say, oh, what is that? Right? So I've replaced that f of hat with C. Okay? And usually this function right here is quadratic. So there's going to be only one maximum. So I take, here is this function, I'm going to derive it out. So I put it in here, and this is what I get. And what is C? What is C? Let's go through this. So I'm going to get rid of this minus 2. So it's going to be y, p, y, x, dy is equal to c times p, y, x, dy. I could take out this c right out here. What is this value right here? 1. So C is equal to that. Okay? What is this? What is this? So you may say, oh, first of all, what is, okay, so we all know that this is equal to 1, right? Oh, I'm falling asleep again. X, Px, what is that? Well, what do we call that? That's the mean. That's the definition of mean. What about this? Obviously, this is going to be. What is the variance usually? What is variance? There it is, right? We know this. This is probably like within page 50 of the probability book. Of course, you know, depending on which probability books are there. This is early stage probability, okay? So if you don't remember, you can pick it up in 1-2 hours. Poof. Okay? Don't have to. So what is that? If I did that, this if I did that, what? Expectation of y, but what is it? Given x, so that's okay. So what do I say regression is about? So what does this mean? Let's look and try to understand what the meaning of this is. I try to give you some insight, and usually people are not interested. Let's go on to the next one. Don't talk about that because I'll just give it to you a little bit. The prediction y of your prediction of for that x, which is I've written as c, is the average label of x. So how is it going to predict c for the, so this is test set x. Okay? Test set x. How is it going to predict my label? It's going to look at the training set and try to find the average of the label and predict that. So let's say I had in the training set, let's say the test set is weight 50, and in the training set I had lots of 50s, 50 with 150 of. So the training set, so the test set is what is the prediction for 50? And in the training set I had 50, and one of the label was 5, one of the label was 1, and for another 50 there was a label for 5, and 3, and so forth. Then my prediction for 50 will be the average of that. That's a little bit of intuition. Okay. Ooh, that's a lot of math, but I think we I think this is not too difficult. Okay, I think you guys can handle it. A little bit more math now. Okay? That's just a little bit more. Now, here I'm going to introduce this thing called maximum likelihood estimate. Maximum likelihood estimate. Estimation. So I take that M, I take that L, I take that E, and do that. MLE. Okay? So, first of all, if you do machine learning, maximum likelihood comes out all the time. What is maximum, or what is likelihood? First of all, you have to understand what likelihood is. Who knows likelihood? What is likelihood? Okay, so you're given data set. So this part is done right here. So I'm just trying to say that regression is finding the conditional probability of the label given x. Okay, that's done. That's done. I'm moving into another one. Okay, and I'm going to look at it and try to compare. Okay, so you're given a training set, n training set, and we also are looking at the same model. And the F sub. This is the same model. This is the same model. What do I mean by same model? I'm assuming this here. Oops. Y is equal to fx plus. I'm staying with this model. But I'm going to take a different approach for my prediction, okay? Different approach. I'm looking at this model. So I'm assuming epsilon there, that stuff. I'm going to look at, as I said likelihood, but actually what I'm looking at is, this is conditional likelihood. Oh, Jesus. You may say, what the hell is this? Likelihood, then he's talking about conditional likelihood. I want you to know what's that. Conditional likelihood. It's defined this way. It's the probability of the label. Okay, conditional likelihood is going to be probability of the label. Okay, given what? Given the input. Okay. So this I have put a bold here, bold Y, representing a vector. Vector of what? All the label in the training set. And you may say, oh, and when I talk about the probability of vector, you may say, oh my goodness, it's too complicated. Why is the vector coming in? You can think about, just for those people, who ask a lot of questions and think about, like, what do I mean by Y here represents all the labels corresponding to x1, y1, y2, yn. What is the probability of a vector y? What is this? What is that? Well, this is the joint probability of y1 and y. That's all it is. Okay. So now I see that, I can tell students if they're nervous or, I ask a question, they're looking at me, then I ask a question, they certainly turn away and look somewhere else. Please don't ask me questions, right? And then I tell them the answer, and they're relieved, and they look at me again. So which means that they understood it. Okay, so that's good. Okay, so conditional likelihood is the probability probability of the label given input. But here, instead of writing the input, I'm using this model. I'm using this model, true model, and I'm representing it this way. I have all of that, and I also know the probability distribution of the noise. Okay. This information given input is the same as this information right here. Given that, then I could write it as now. Conditional, so the important thing is conditional likelihood is the probability, the joint probability of owning the label. Okay, given the input. Okay? Now, in machine learning, we always make this assumption, and it's not always true. We always make this assumption. Can someone tell me what that assumption is? No. We assume that each data, this pair, is independent of all the other ones, and they are identically distributed. Remember what I said? These pair comes from what distribution? Joint probability distribution of P, X, and Y. It's some joint probability distribution. In machine learning, it's always good to think that there is some probability distribution. They're all coming from the same probability distribution. These are samples. Okay? And they are independent now. Each sample points are independent, meaning that one sample is not looking and says, hey, what was I equal 5? Oh, learning, I5 was this, so I6 is going to be something. It doesn't do that way. You don't care. Each one just comes out independent. Okay? So we can write it this way. We can write it this way. We can write it as the product of each one. And someone said Gaussian. I said no. But the Gaussian is here. Why is it possible that I write Gaussian? This N stands for normal, right? Gaussian. Why is it Gaussian? No, look at this. No, not everything's Gaussian. Look at this. The error was Gaussian. Okay, so I don't understand how that Gaussian and this Gaussian is. Can someone tell me? Why is the label Gaussian? The noise is Gaussian. Huh? So what I'm saying is epsilon is 0 means sigma squared. What about f of x is deterministic? What about y? It's a Gaussian with what mean what? F of x varies sigma squared. Right? Everyone says this is Gaussian, it's random. This one is deterministic, right? So what is that? That's a Gaussian, but where is the Gaussian? Centered at f of x. So that's why I can put a Gaussian on each one of them. Because the noise is Gaussian, right? You understand this? Okay. Now, when I work with Gaussian, Gaussian is exponential of some quadratic. Alright? Gaussian is in the form of exponentials of some quadratic function. Well, exponential is a nuisance. I want to get rid of that exponential. I want to try to make it polynomial. I'm more comfortable with polynomial. So what do? I take the log. Oh my goodness. I take the log. That. I get that. And usually this is called the log likelihood. You know, machine learning, it's actually log conditional likelihood because you got a data label, but people just call it log likelihood. Okay? And this, people just call this the likelihood. But we're really putting the probability. And what is this? I mean, this is saying, what is the likelihood of getting that label? Well, what is the likelihood? Well, what's the probability? The likelihood is like the probability. So you get that, and you get this. ED represents that. So it's just doing this, and putting it in it, and then you get that. What do you want to do? What do you want to do? Now, I've represented, I got the training data now. There's training data in here. I found the likelihood. What do I want to do with the likelihood? Yes. I want to find these predictions, this f of x, or these parameters, such that my probability of observing that y is high. No? These are the values, these are the things that I'm trying to find out, right? I want to find out these things so that this is, and it turns out, if you look at this, so maximizing the log likelihood is the same as minimizing this term, which is minimizing the mean square. Okay? So we looked at this formulation. We looked at this formulation, mean square error, minimizing the mean square error. We are looking at maximizing the likelihood. And we arrived at this. So next time, are these things all different? What are the relationships? One loss is this. One approach is that way, the other approach is, the one approach is mean square error, approach this way. Another approach is looking at the likelihood. It's another approach trying to find what is it trying to find the W's? We're trying to find the predictions, not W's, predictions. And all of this, we'll try to tie that in. Okay? Okay, any questions? Okay, no questions, then I